All right. Today we're going to talk about basic facts about electromagnetic propagation theory. We're going to look at layers of the atmosphere, and more specifically, layers within the ionosphere. We have some definitions: reflection, refraction, diffraction, angle of incidence. Just discussed that with your near vertical incident. That's what it's talking about, is the angle of incidence. Atmosphere attenuation, multipathing, anomalous propagation, path loss, free space loss, and then we'll just briefly look at a transit. The Earth's atmosphere, as you learned way back in school, is made up of different layers. The only two layers we're concerned with in RF is the troposphere, which is the lowest layer. That's where all your weather and stuff happens. And then the ionosphere, that is ionized by solar radiation, and we use that for your HF. The troposphere, the lowest layer, is where your weather is. So there's a high volume of solids and liquid particles, dust particles, pollution, moisture particles. That's the layer we live in, and it's actually used for a form of communication called tropospheric scatter, or tropo. We'll look at that a little more in a minute. The ionosphere is the one we use for HF. It's about 30 to 600 miles above sea level. It's called the ionosphere because it's ionized by solar radiation. It's actually got layers within the ionosphere layer. It's got three basic layers. You have your D layer, which is the lowest and densest layer. And above that, you have the E layer. And above that, the F layer. Those all are there in the daytime because they're caused by ionization. The F layer is always there. The D layer, lowest and densest layer, is only there in the daytime. The E layer, the daytime, it becomes more dense, and then it thins out and can disappear at night. F layer during the daytime can become denser and divide into two separate layers, F1 and F2. The reason you get your D layer and your E layer and F layer dividing into two layers in the daytime is that's when the sun is up and you have a lot of ionization. The F layer is always there, which is a good thing, because that's the layer that we use for beyond line of sight skyways, long range. Depending upon the time of day, you're going to have an optimum or a best frequency. Also, depending upon the time of day, you may have some frequencies that don't want to work, such as in the daytime when you have, oh, I got my D and E here switched. When you have a lot of ionization, and you have the D layer, and you have the E layer, and your F layer divides into F1 and F2, well, your lower end of your HF, a lot of it will get absorbed in the D and E layer. They never reach the F layer for long range communication. So in the daytime, the lower end of HF sometimes doesn't work as well. Excuse me. But that's okay, because the high end of your HF will work. It can penetrate these lower layers, reach the F layer, where it can be reflected back for that long haul communication. Now, what's a high end frequency and what's a low end frequency? There is no specific answer. Basically, it's if it's the daytime, you're using 15 megahertz, it quits working, then you may want to go to a higher frequency. Watch this. I'm proud of this. Sun goes down. Ionization decreases. You lose the D layer. D layer can thin out or disappear. Your F layer thins down to just one layer. This is at night. The sun sets, no more ionization. So now those low end frequencies that didn't want to work in the daytime, with that D layer gone and that E layer practically non-existent, the lower frequencies now can reach the F layer for that beyond line of sight communication. A higher end of your HF, higher end frequencies with a shorter wavelength, with no D layer or E layer, when they reach that F layer and it's thinned out, they can just penetrate and keep going right out into space. So at night, the lower frequencies in the HF band tend to work better. And in the daytime, the high-end frequencies within the HF band work better. At any particular point in time, and for a particular communication shot, you're going to have a lowest usable frequency. And it's exactly what it says, is the lowest frequency you can use in your receiving terminal get an acceptable signal. If you go below that frequency, the signal becomes unusable. You also have a maximum usable frequency. That's going to be the highest frequency you can use at that time where your receiving station's going to get a usable frequency. Now, somewhere in between the lowest frequency and the maximum frequency is going to be your best frequency, and it's normally between 80 to 90% of that maximum. That best frequency is called your optimum, or your frequency of optimum transmission. That's the best operating frequency for a given transmission path at a specific time. That's going to give you your best reflection off that F layer. Now, that's determined by the time of day, amount of ionization in the ionosphere, where you're located, the season, whether you're holding your little pinky finger correctly. So it changes. What might be your optimum frequency at 2 o'clock in the afternoon may not be the optimum frequency at 5 o'clock in the afternoon. Angle of incidence. If you were to go up into the ionosphere and drop a plumb bob straight down, then you would have this nice straight line running vertical between the ionosphere and the ground. Now, you come over here and you have your antenna, and you transmit your signal up to the ionosphere. Well, where it interconnects with your plumb bob, that's where you get your angle of incidence. It's the angle formed by a wave, in this case your RF, striking a surface and a line perpendicular to the surface at that point of incidence. Okay? So there's your angle of incidence. If your angle of incidence becomes too up and down or too high for a particular frequency, it can penetrate the ionosphere. If it's too sideways or too low, then it may just get absorbed and not be reflected back down to your receiving station. Now you have a critical angle, and a critical angle is different for every frequency, and it's going to be different depending upon the conditions of the ionosphere. But the critical angle just means that if you exceed that angle, then your signal is going to be penetrating the ionosphere. So here you can see the signal's going right on through. So I've exceeded my critical angle. You all know what a reflection is. You see it every morning when you look in the mirror. You see your beautiful little reflection smiling back at you going, oh, yay, another Air Force morning. I get to go do lab in the heat and the humidity. A reflection is where the wave bounces off a surface or an obstruction, such as the ionosphere. RF in the HF band will hit that F layer in the ionosphere and be reflected back down to Earth. That's how we get our HF communication. Now, the angle that it gets reflected back down to Earth will equal the angle of incidence. So it's an actual law. Angle of reflection will equal the angle of incidence. I drew those pictures, so you can just go ahead and tell me how wonderful they are.
They're wonderful, man.
Thank you. I needed the accolades. Refraction. Refraction is a change in direction of propagation of a wave due to a change in its transmission medium. Okay, so here your signal is going through the atmosphere and it hits the D layer, which is really dense. It's been ionized heavily. So that's going to cause your signal to bend because it went from one medium into a different medium. Here you see the straw in the glass of water. Here you're looking at the straw in air. Here where it enters the water, light rays change because the density of the water is different from the air. So it bends what you're looking at. The straw is actually still in the same place, but it bends it as far as what you see. So your RF rays, just like these light rays, will actually bend. They go from one medium into another. Sometimes they bend the way you want them to. Sometimes they can actually bend the opposite direction and go out into space. How much bend you get is going to be dependent upon the conditions of the ionosphere, your incident angle, what frequency you're operating at. So if you change to a different frequency, you get a different amount of refraction. Diffraction is the bending of a wave when it encounters an edge of a building or the edge of a mountain, or when it encounters a constriction, like it's trying to go between two buildings or two mountains. So diffraction is the bending of a wave as it encounters a constriction or an edge. Now, your lower frequencies are more prone to diffraction because of their longer wavelengths. You can think of diffraction as you're walking along the ground and all of a sudden there's a log in front of you and you don't see it. You catch your toe on it and your body diffracts face first into the ground. It's exactly what happens to the wave. The wave, part of it catches on a building or catches on a mountain, and it bends or diffracts that wave. Atmosphere attenuation, sometimes called absorption, is just your signal being degraded by the conditions in the atmosphere. The primary cause is moisture. Moisture comes in a lot of different forms. It can be in the form of clouds, it can be rain, it can be fog, humidity, and other things that cause that absorption or atmosphere attenuation is the different gases and random particles that are in the atmosphere. Now, I'm sure most of you have been in heavy fog at one point or another, and you know everything sounds different because it gets attenuated by the moisture in the fog. Any questions so far?
I got nothing.
Is that a yes and no?
No.
No, ma'am.
No, ma'am.
If you have a question, this is the time to ask them, okay? When I ask you if you have a question, if you have one, speak up. Atmosphere attenuation, as your frequency increases, your attenuation increases. Your frequency goes up, the wavelength goes down. So those I can't talk now. Those moisture particles and particles of dust and pollution are going to affect the smaller wavelengths more than the longer wavelengths. So the higher up in frequency you go, the more it's affected by atmosphere attenuation. Tropospheric scintillation, talking about in the troposphere, you have all that moisture and dust and pollution and humidity. Well, all of that has a tendency to form little pockets of warm air and then a pocket of cooler air, and maybe you have a pocket of heavy humidity, and then it goes into a drier pocket. Well, as your signal travels through those different pockets, it's going to speed up or slow down depending upon density and all of the makeup of that little space that it's going through. Now, SHF and EHF are your most affected. Multi-path propagation, talking about your signal taking multiple paths between your transmitting antenna and your receiving antenna. It creates what we call fading. It occurs when your RF signal leaves your transmit antenna and it doesn't all follow one straight path to the receiving antenna. Some of it may get reflected, some of it may go up into the ionosphere, some of it may run into a building and get diffracted. So there's all kinds of things that can happen to your signal when it leaves the transmit antenna before it gets to the receiving antenna. Now, the signal that had the most direct route is going to get there first, and it's going to be the least affected. And then the other parts of your signal are going to come in, and you can see here by looking at this picture that there are different amplitudes and different phases, and that's because they travel different paths. So when they come together in the receiver, you actually end up with something that looks like this. Your previous blocks, one of them, you had a block diagram of the receiving side of your radio. And you had something in there that was used to keep your received signal constant, even though it varied at the input to your receiver. Anybody remember what that was?
Are you talking about the filters now?
No. It keeps, what it does, I missaid that. It keeps the output, so your output signal, your voice, if someone is talking and that's what you're demodulating, you want that voice to remain at a constant volume. But the input to your receiver is constantly changing. So what was in that radio receiver that would keep your voice coming out the demodulation process constant, even though the input to your receiver was changing?
With the automatic gain.
Exactly, the automatic gain control. Well, here is why you need an automatic gain control. The signal coming into that receiver is not going to be one constant, perfect signal. It's going to have all kinds of variations, and it's going to fade in and out. It's going to get weaker and stronger. So your automatic gain control compensates for that, so your end product can remain at a constant voltage or a constant amplitude. Anomalous propagation. What's an anomaly?
Something that's not you.
Okay, so anomalous propagation, it just means that our propagation paths, they don't follow a straight line. They have different variations in density and obstructions and moisture that they're going to go through. These are all anomalies. Reflection, diffraction, refraction are all examples of anomalous propagation. The anomalies are going to affect
Good morning,
your signal.
y'all. Putting
You
this
can
video
reflect it,
together.
diffract it, refract it, absorb it. So those are all anomalies. Free space. Theoretical perfect space is void of gravitational and electromagnetic fields. We're not operating in a theoretically perfect space. But when we talk about free space, we're just talking about a path clear of obstructions. This is your SATCOM antenna, and it's transmitting to this satellite. You know you have to have a line of sight or a direct path to that satellite. So between your transmitting antenna and the satellite is free space. There's no trees or buildings or anything in between here. That's free space, a path clear of obstruction between your transmitting antenna and your receiving antenna. Now, even though there is nothing between this transmitting antenna and that receiving antenna to mess with your signal, there's no trees, there's no buildings, you're still going to have a path loss. Excuse me, you're still going to have what's called free space loss. And free space loss just means in all of that free space, there's nothing there to interfere with you, you're still going to have a loss. And that loss is caused by once your signal leaves this transmitting antenna, it starts to spread out. As it spreads out, it's spreading its energy out. Think of a flashlight. You turn on a flashlight, the light comes out of your flashlight and it starts to spread out. As it spreads out, it gets dimmer. Same thing here. The signal comes out of the antenna, it spreads out. As it spreads out, the amount of energy at any one spot is less. That's free space loss. Reduction in signal strength as your energy disperses or spreads out as it radiates from this transmitting antenna to the receiving antenna. It does not factor in anything environmental, strictly just the signal spreads out. So because there is so much space between your SATCOM antenna on the ground and your satellite, free space loss is the major loss for SATCOM. Now, path loss, just plain old path loss, factors in everything. Is the total power lost between your transmitting antenna and your receiving antenna, irregardless of what caused it. It's the difference between what you transmitted and what they received. Everything is factored in, okay? Including free space loss. So path loss includes everything that messes with your signal, including free space loss. So free space loss and atmospheric attenuation are the two main causes of path loss. Have y'all used a transit yet?
No, ma'am.
Okay. When you do your SATCOM antenna, you're going to be using the transit. And it's similar to a compass, but it does a lot more things. But we use it to find azimuth and elevation. Azimuth is that side-to-side angle, which you can turn something 360 degrees. Elevation is an up and down angle. You can only go up 90 degrees. Well, then you start going back down again. The azimuth and elevation of your antenna is called the look angle. Here's what the transit looks like. You have two levels. One's a bar level, and you have this circular level. This is called a sighting arm. Now, this circle level, when the bubble's in the middle, that just means that you are holding the transit level. Okay? It lets you know you're holding it level. And you need to hold it level because here is your needle. Just like a compass, it has a north seeking end of the needle, and it always points what direction?
North?
What direction is the north seeking end of your needle going to point?
North?
Magnetic north?
It always points what direction? Think of a compass.
North.
The needle always points where?
North?
Is it
North.
north, ma'am?
Okay. So in order for that needle to point north, it's got to be able to spin freely here. And so that's why you have to make sure you're holding it level. That's the purpose of that bubble. You know you're holding it level. Your needle can move freely. Now, no matter which way you turn this transit, that needle is always going to point north. Okay? So when you want to find the direction to point your antenna, if you're told it needs to be at 78 degrees azimuth, you're going to rotate the transit in your hand until the north-seeking end of the needle is on your desired azimuth, in this case, 78. So when you put it on 78, now this sighting arm points the direction you want your antenna oriented. Okay? And you will be doing that when you put up the SATCOM antenna, the AV2011. Now, elevation, you do a little differently. You're going to hold the transit sideways. Excuse me. Oh, by the way, your 360-degree scale is out here on this outermost ring that you use for finding azimuth. Finding elevation, elevation only goes up to 90 degrees. Here, 90, 0, 90. So we're going to be using this scale in here to find elevation. We're also going to be using, I forget what this is called, but it's a movable arm and it has a little scale. I think it goes from 30 to 0 to 30. 0 right here in the middle is what we're interested in. There's a little thing on the back of the transit that you can move, and when you move it, it moves this. It moves this whole thing around that area right there. Okay. So now, if you line the 0, that up with the 0 on your 90-degree scale, then set your transit down on its side. This bubble should be level, indicating that you are directly horizontal to the earth. Okay? That's what this bar is used for. You get the bubble right there, then you are holding it level with the Earth, which would be 0 degrees elevation. Oops. So if you wanted an elevation of, say, 45 degrees, you would move this little arm with the 0 on it. You would move it so the 0 here matches up with 45 degrees. Then you would simply raise the transit until this bubble is in the middle again. And then that would be pointing your 45-degree angle. And you will do this when you do the AV 2011, and you'll actually have one, and they'll show you how to use it. Okay, so do we have any questions on what we just covered? Hopefully you got this better than you did antennas.
Yeah, it's pretty straightforward. It's just absorbing it now at this point.
And that just, everybody absorbs it at a different rate. So each person just has to do what they need to do to get the material.
Flashcards usually help.
Pardon?
I was just saying I use flashcards. That normally helps me.
And flashcards are great. I always recommend flashcards. And Mr. Mayer is recording this, and he's going to put it up. He recorded the one this morning, and he's going to put both of them up. It's the same material, but you can go in and look at it again if you have questions, or you can send a question through chat. Okay, so any problems with this? Everybody understand it?
Yeah, I'm good to go. I'm just going to read over it a few more times.
Okay, so we're going to go ahead and do 1D. Oh, and by the way, Mr. Mayer put the appraisals up in the resources for Block 4, and we will go over those on Tuesday. Okay, so get all your appraisals done, and then Tuesday we will go through them, and that will also work as a good review before you test. You test Wednesday, correct?
I
don't think so.
thought we tested Friday because we have a 4-day weekend.
We don't test Friday, 'cause I believe Friday's a down Friday, isn't it?
Well, this Friday is.
This Friday's a down Friday, so next Friday is, I believe, when I wrote it on my schedule, factoring in the 4-day weekend, I believe we test on Friday.
Okay, well, Tuesday we'll go over the appraisals, and then we'll learn at that time if you want to meet on Discord again before you test. Okay?
Okay. Mrs. Irwin?
Yes.
When did you want to break for lunch, by the way? Just a reminder, I believe they close at 12.
Oh, the other day y'all said they were open till 1.
Yes, ma'am. I
Azalea's
believe
open
it's
till
still
1.
1300.
Okay. This next one's really super short. Okay, we'll go through it really fast.
Okay, no problem.
Well, it is a problem if you don't get lunch.
I think Magnolia closes at 12 and Azalea is open till 1300 or 1330.
Okay, we'll hit this really fast. RF Spectrum Interference Resolution Program. Spectrum interference disrupts operations of your communications or of electronic device operating in the RF range. Now, interference can be from your enemies deliberately trying to interfere, or it could just be somebody has no idea they're causing an interference, or it can be from natural causes such as solar flares, northern lights, or lightning. Of course, the Air Force has a program for everything. So if you have interference issues, we have the U.S. Air Force Spectrum Interference Resolution Program, and it provides guidance on methods to resolve interference problems. You always want to solve your interference problems at the lowest level, except Your unit is under operational control of a combatant command. You don't want combatants out there and you not providing communication. So if you're under operational control of a combatant command, then you are going to immediately upgrade the problem or upstream the problem. Interference can be caused, again, by enemy, neutral force, friendly forces, natural devices. It can happen in the U.S. or inside a host nation during times of just no combat, or if you're in combat. It can be something as just an electrical current you pick up on your equipment to a complete enemy jamming. Natural causes, solar flares and northern lights, cause radiation which can interfere with your electronic equipment. A little man walks through, he's going to have some interference because this high-powered signal from the dish is probably going to interfere with what he's trying to receive in his little antenna. Okay? So that could be some unintentional interference. Or maybe this dish is interfering with this horizontal dipole. Okay? So operation of an electronic device disrupted by an EM field of an external source. It can degrade the performance of your circuit or completely block your communications. If you are a victim of electromagnetic interference, there is an AFI for that. You're going to accomplish the preliminary actions outlined in paragraph 3 of AFI 17-221. You also contact your local installation spectrum manager. Most interference, you're going to be able to look around and see whatever the problem is. Okay? But if you can't readily solve the problem, then your installation spectrum manager is going to upgrade it to the MAGCOM spectrum manager. Well, again, if you're under the command of a combatant unit, you're going to go to MAGCOM directly, right at the beginning. All interference is going to get resolved on a case-by-case basis. Sometimes it's as simple as walking out and going, oh, they parked their truck in front of my antenna, to having to spend days trying to track down where the interference is coming from. So spectrum interference disrupts operations of an electronic device operating in the RF range. It can be intended, unintended, or from natural causes. Resolving it begins by accomplishing the preliminary actions outlined in paragraph 3 of AFI 17-221. You want to solve your interference issues at the lowest possible level, except when your unit is under operational control of a combatant command. Then you take it up channel immediately.